Hi everyone, my name is Nicolas Samardžić and it's my great pleasure to be here and to introduce CraterLake, a hardware accelerator for efficient unbounded computation on encrypted data. I was lucky to work on this project together with Axel Feldman, Alexander Krstev, Nathan Manahar, Nick Janice, Professor Srini Devadas, Karim Eldafravi, Professor Chris Preikert, and my advisor, Professor Daniel Sanchez. CraterLake is a hardware accelerator for fully homomorphic encryption, or FHE. FHE is a cryptographic technique that enables computation on encrypted data. This means that we can use FHE to execute computations in the cloud without sacrificing any privacy. But nothing good comes for free. The main problem with FHE is that it is 10,000 to 100,000 times slower than performing the computation directly on unencrypted data. FHE's computational primitives do not map well to existing hardware, like GPUs, because they exhibit complicated all-to-all dependencies. And while prior FHE accelerator designs speed up smaller FHE programs by 5,000x, they remain inefficient on large programs, like deep neural networks. CraterLake is the first FHE accelerator that is effective on FHE programs of any size, providing 5,000x speed up over a 32-core CPU and 11x over prior accelerators. So in the CPU, a ResNet 20 inference on encrypted data takes over 20 minutes, and CraterLake brings this down to 250 milliseconds. Plaintext vector in FHE consists of tens of thousands of real numbers. An FHE ciphertext holds an encrypted plaintext and is composed of two high-degree polynomials with large integer coefficients. For example, 64k-degree polynomials with 1600-bit coefficients. This implies a 25 megabyte ciphertext. Note that CraterLake does not accelerate this encryption, but instead accelerates the computation on FHE ciphertexts. FHE supports three operations on the underlying encrypted vectors: element-wise multiplies, element-wise adds, and cyclic vector rotations. This doesn't mean that a multiplication can be implemented by simply multiplying the polynomials of the two ciphertexts. To implement an FHE operation, we must actually perform many primitive polynomial operations. Specifically, FHE requires support for element-wise modular additions and multiplications, and two more complicated operations that have all-to-all dependencies: automorphisms, structured permutations on polynomial coefficients, and number theoretic transforms, or NTTs, used to speed up polynomial multiplication. All FHE operations can be implemented using these four primitives. The illustration shows the primitive operations we must apply to implement a ciphertext multiplication of ciphertexts x and y. Key switching is an FHE algorithm composed of hundreds and sometimes thousands of primitive operations. Thus, key switching is responsible for over 90% of compute in most FHE programs and is FHE's key kernel. We will come back to it throughout this talk. Let's now discuss challenges specific to large FHE programs. The bottom line is that large FHE programs require ciphertexts that are up to 10 times larger than what prior work supports. Let's see why. Ciphertexts start out with a small amount of random cryptographic noise that guarantees the privacy of the encrypted data. As we apply operations on the ciphertext, this noise grows. Noise growth must be trimmed during computation, which as a side effect reduces the ciphertext's footprint. This illustration shows the ciphertext getting smaller during execution of an FHE program. This sounds good at first, but ciphertexts cannot get too small or they will become undecryptable. So does this mean that FHE programs are limited in their depth? Fortunately, this issue can be circumvented by bootstrapping, an FHE procedure that refreshes the ciphertext back up to a larger size, thus enabling more computation. This means FHE can support arbitrarily deep computation by separating the program into regions of limited depth and bootstrapping in between. But as the slide shows, bootstrapping requires working with large ciphertexts, which prior work does not effectively support. Therefore, prior work is limited to programs that are shallow enough to not require bootstrapping. Note that the y-axis here shows the footprint of a single ciphertext, and getting good operand reuse may require storing many of them on chip. By supporting sufficiently large ciphertexts, CraterLake enables accelerating arbitrarily deep FHE programs. Targeting these large ciphertexts requires new architectural and algorithmic techniques. Let's dive into the architecture first. Both CraterLake and prior work employed the residue number system, or RNS, to implement modular arithmetic. RNS leverages the Chinese remainder theorem to represent large integers as many smaller integers called residues. The magic of RNS is that now a multiplication of two 1600-bit numbers can be implemented as an element-wise multiplication of the corresponding residues. And addition works the same way. This means arithmetic is significantly cheaper in RNS than operating on large integers directly. This idea also works for polynomials. A polynomial with 1600-bit coefficients can be decomposed into many residue polynomials, each with word-sized coefficients. Polynomial multiplication can then be carried out per residue polynomial pair. Let's see how F1, the state-of-the-art FHE accelerator, implements an NTT on a large polynomial and why its approach does not scale. As mentioned, large coefficient polynomials are divided into many residue polynomials. Thus, to implement the NTT, we just need to apply the NTT to each of these residue polynomials. Now, we've mentioned these residue polynomials have tens of thousands of elements, so a wide vector processor seems like a natural fit. Fortunately, NTTs and automorphisms have complicated all-to-all input-output dependencies. So instead, F1 is designed as a multiprocessor with many identical compute clusters optimized for residue polynomial arithmetic. The clusters are connected by a flexible on-chip network that supports all-to-all communication between clusters. F1 schedules an entity of a residue polynomial onto a single cluster. This allows F1 to resolve an entity's dependencies locally within a cluster. To achieve high performance, F1 schedules many entities in parallel across its clusters. While this approach works well for entities and automorphisms, it fails during key switching, which is by far the most expensive sub-procedure in FHE operations. This is because the number of dependencies between residue polynomials in key switching is quadratic in ciphertext spot size. All residue polynomials of the output depend on all residue polynomials of the input. This means that network communication will also be quadratic in ciphertext size, because F1 localizes entire residue polynomials to individual compute clusters. This makes large ciphertext required for deep FHE programs especially deadly to F1's design. To make scheduling easier, F1 connects its clusters with the flexible all-to-all on-chip network. But this flexibility comes at a high area and power cost. Lastly, even with this flexible network, scheduling for F1 is a very hard problem. This ultimately results in poor utilization. So, what does CraterLake do? Well, it actually does what I told you is a bad idea in the previous slide. CraterLake has the entire chip work on one residue polynomial at a time, a vector uniprocessor approach. Because residue polynomials have tens of thousands of elements, it is not hard to keep the entire CraterLake chip busy on a single residue polynomial operation. CraterLake has 2048 lanes and features a heavily banked 256 megabyte register file, which is necessary to enable good reuse of FHE's large operands. The animation shows how an entity is applied in CraterLake. The entire chip applies the entity on one residue polynomial at a throughput of 2048 elements per cycle. So how can all this be implemented? CraterLake's physical organization consists of 8 lane groups. Each lane group stores and processes its fair share of the elements. Thus, lane group 0 works on elements 0 to 256. Lane group 2 works on elements 256 to 512, and so on. This data layout prevents the dependencies between residue polynomials from overwhelming the network. Each lane group stores the same coefficients of all residue polynomials. This allows CraterLake to resolve dependencies across residue polynomials locally within each lane group. So the bulk of key switching is local to each lane group, sidestepping F1's main scalability issue. But there's a problem. With this design, entities and automorphisms require network communication because they induce dependencies between different elements of the same residue polynomial. F1 didn't have this global communication problem. So why is CraterLake's approach better? Well, first, making dependencies between residue polynomials local and dependencies across residue polynomial coefficients global is a worthwhile trade-off. This approach makes communication between lane groups grow only linearly with ciphertext size, instead of quadratically like in F1. Second, it enables us to design a novel on-chip network that is fixed and requires no control logic. These two insights are key in making CraterLake's uniprocessor design practical. Indeed, CraterLake's network is 16 times smaller than what an equal performance F1 design would need. Let's see why CraterLake's network can afford to be fixed. We've mentioned that there are two polynomial operations in FHE that induce dependencies between coefficients, entities and automorphisms. The good news is that these dependencies can all be resolved using a fixed function matrix transpose. This means the network can be implemented using only wires and requires no control logic. The figure here shows the exact fixed permutation the network needs to implement for a 4-lane group design with 4 lanes per group. Now let's motivate and introduce CraterLake's microarchitectural contributions. Scaling to large ciphertext presents additional architectural challenges, specifically with respect to key switching, FHE's key kernel. Prior accelerators target the standard key switching algorithm, but this algorithm does not scale to large ciphertexts. Boosted key switching, a newer key switching algorithm, scales much better in terms of compute and, most importantly, footprint. In particular, standard key switching's footprint can be as high as 1.7 gigabytes, far too large to fit on chip. In contrast, boosted key switching's footprint is only 52.5 megabytes. Boosted key switching is not our contribution and is an algorithm already adopted in FHE software libraries. However, CraterLake is the first accelerator to target boosted key switching. Hardware designed for standard key switching cannot support boosted key switching effectively. Most compute in standard key switching is concentrated in entities, which contains an order of magnitude more compute than the polynomial multiplies and adds. Prior hardware supports entities well, but the vast majority of compute in boosted key switching is actually in multiplying and adding polynomial coefficients. Because of a large number of simple operations, a naive implementation of boosted key switching would be bottlenecked by register file bandwidth. To address this problem, we designed the Change RNS-based unit, or CRB, a functional unit that encapsulates most of the simple operations in boosted key switching. The Change RNS-based unit is made up of many parallel multiply-accumulate pipelines that exploit the high internal reuse of the inner loop of boosted key switching. This approach allows for a much higher throughput than independent multipliers and adders communicating through register files. This is the same insight behind DNN accelerators like the TPU and tensor cores in GPUs. Since key switching is made up of long pipelines of polynomial operations, it's amenable to vector chaining, which we employ to reduce register file pressure by a further 3.5x. And we reduce memory bandwidth requirements by designing the KSH-gen, a functional unit that generates a large part of FHE's operands from a very small seed. Please see the paper for details. We use 4 deep and 4 shallow programs as benchmarks to evaluate CraterLake. Deep benchmarks are those that require bootstrapping and include ResNets and LSTMs. Shallow benchmarks do not require bootstrapping and are thus limited to neural networks with 3 to 6 layers. All programs come from state-of-the-art software implementations and use the CKKS scheme. We implemented CraterLake's components in RTL and synthesized them in a commercial 1412 nanometer process using state-of-the-art tools. We target a configuration with area and power budget similar to a modern GPU or server CPU. The table shows CraterLake's area and the breakdown by component. Overall, our CraterLake configuration requires 472 millimeters squared. We compare CraterLake to baselines with similar area and power budgets, a 32-core server CPU, as well as F1 Plus, a scaled-up version of F1. The table here reports the performance on CraterLake on deep and shallow benchmarks measured in milliseconds. CraterLake achieves very large speedups over the CPU implementation, ranging from 2900 to 8600x. Speedups are similar across deep and shallow benchmarks, showing that CraterLake provides robust gains across FHE program types. We also compare CraterLake to F1 Plus, a scaled-up version of F1. CraterLake achieves large speedups over F1 Plus on deep benchmarks, outperforming it by G-mean 11x and up to 18x. By contrast, CraterLake and F1 Plus achieve comparable speeds on small benchmarks with a G-mean speedup of only 30%. These stark differences demonstrate that prior FHE accelerators are efficient only on shallow computations and falter on deeper ones. The per-benchmark power breakdowns show that CraterLake uses most of its energy on compute, despite FHE's data movement challenges. This indicates that FHE is a great target for hardware specialization and that outperforming CraterLake without fundamental cryptographic or algorithmic advances would be hard. CraterLake also achieves high utilization across benchmarks. To conclude, for widespread adoption of FHE, accelerators must efficiently support all FHE programs. CraterLake is the first accelerator to achieve this. As a result, CraterLake enables new applications for FHE, such as real-time inference using deep neural networks like ResNet or LSTM. Thank you for your attention, and I look forward to answering your questions.